Hi. Okay, so we're going to start the day 2 conference. I hope you had a good night rest yesterday night. And we're going to start with a sponsor's presentation. So we have all the sponsors lined up to speak. And without them, this conference would not have been possible. And letting you know that we have 3 lottery ready and another 3 ready for brainstorming competition. And for prizes, we have $50 Apple gift card.
Whoa.
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 And we have robot brought from ABB.
Whoa.
Whoa. And there's another robot.
Even more.
So, yes. So after sponsor's presentation, we're going to draw for robot. And after lightning talk, we're going to draw for another robot. And after poster session, we're going to draw one for $50 Apple gift card. Okay. All right. So the first up, from Kristin Mccartney from IEEE University Partnership Program. So welcome, Kristin, please.
My name is Kristin Mccartney. I'm a staff member at the IEEE. I just celebrated my 10th anniversary, and it's been, in many ways, the best thing that ever happened to me to be part of that organization and to get to meet people like you over the years. I don't have a lot I want to say. I just want to say what an incredible privilege it has been to work with the MIT IEEE ACM student branch and with the Boston section. I've known Bruce and Soon and Rob for a while. They're people who do what we call bleed IEEE blue, and I'm very grateful to have this little close relationship with them. I'd also like to thank May and Stephanie and Anthony and Alyssa, because they have been an incredible source of labor for us and inspiration, and we enjoyed their presentation last night. Special thanks to the sponsors. I mean, we would not have had quite the elegant conference that they were able to put on without their contributions, so please pay attention to them when they come up after me. You did ask why I don't have a slide, and it's because I have about 350 slides, because there's so much about the IEEE that I can talk about. To me, it's first all about the people, and IEEE connects people to other people. It connects people to information that enhances their lives and their careers, and it connects people to opportunities. And the opportunities are just exploding through the efforts of our volunteers, and some of the staff back at the operations center, at our facilities around the world. And for those of you who don't know me, I left business cards out on that table. And if you ever need someone inside the IEEE, it can often be hard to navigate who's the right person to talk to. You have a question, you have a suggestion. I'm offering myself up to be that person who can potentially go knock on a door and get a response for you if you're having trouble finding who you need to talk to. So without further ado, on to the sponsors.
I'm Dennis Shapiro, chair of the Boston chapter of the Consumer Electronics Society. I'm a member of the Society's Board of Governors. With me is Sunish Gupta on my right. He's also a member of the board, and he'll say a few words following mine. In earlier years, the consumer electronics was audio, radio, TV, hi-fi, and Boston was the home of some of this. Maybe you know that the Alexander Graham Bell worked in Boston when he was developing the telephone. And in Boston, our history is continuing through the world of hi-fi. Very famous traditional loudspeaker design, and of course, Boston's the headquarters of the Bose Corporation. Today, because of connectivity, consumer electronics seems to have few limits. One is tempted that all electronics are personal, and what is not is infrastructure. But the bottom line here is that consumer electronics seems to be where it's at. And IEEE Consumer Electronics Society is the premier technical association of the consumer electronics industry. We work closely with the Consumer Electronics Association, which runs the Consumer Electronics Show in Las Vegas each January. How many people here have been to CES?
Woo! Yes.
That's terrific. CES is like the mecca of anyone who wants to be in electronics or computer sciences. Everything is there. If you haven't gone, you have to go. It has to be part of your basic education. So I hope you'll plan on doing that. The CES is in Las Vegas each January, and there are other shows that it supports in Europe and Asia. A number of these shows have an associated technical conference organized by the Consumer Electronics Society. The conferences provide the opportunity for you to present papers and to publish. Talking about publishing, the Society publishes the Consumer Electronics magazine, and I just got my latest copy, which is terrific, and guess what? I forgot it. It's sitting by my door at home, but it's kind of CE Society's shot at being like the Scientific American of consumer electronics. It's a new publication, getting better and better every month, and the magazine comes free with membership. So talking about membership, we have a conference special, and maybe you've seen the announcement on the wall, but we have free Consumer Electronics Society membership for 2016 to student members of IEEE. Instructions are posted on how to apply, a simple email with your address and IEEE member, and a member number, and the email address is Boston CE SOC. It's BOS CE SOC, not Boston, just BOS, at gmail.com. And you get that, and you'll be signed up, and you'll be getting our publications and be members of the society. Now, there's one thing I learned, having been a member of IEEE since before most of the people here were born. I originally joined in 1952, and I kept my membership going. And all of a sudden, one day, I got a letter in the mail that says, "You are now a life member." And I said to myself, what's a life member? I looked it up. And a life member means no more dues for the rest of your life, which sounds terrific. Now, how does it work? It's a total of the number of years you've been an IEEE member, and your age has to equal a certain magic number, which may be 100, I'm not sure. So it is.
Yeah, your age plus the number of your membership equal to greater than 100 years.
There you go. So I'm saying that, remember, every year that you renew your membership, it's like a Social Security. You're adding to your retirement benefits, and that's terrific. And you should be thinking about that. And life expectancy is on your side. So there you go. I want to introduce my colleague Sunish Gupta, who is a specialist in accessibility, and he's doing some wonderful work. Sunish, come on here, stand in front of the microphone.
Thank you, Dennis. Yeah, I mean, as Dennis said, it's a very exciting time to be part of the electronics revolution. It didn't begin yesterday, probably began day before yesterday. So, well, first of all, let me thank everyone who is here on a Sunday morning. Being a student, it's not easy to get up, 7 in the morning on Sunday morning and come, but I'm very happy to see everyone of you over here. So IEEE, I have been issued with IEEE for last 25 years. As soon as I did just about when I was doing a bachelor's, I joined the IEEE as a student member. And believe me, I mean, I used to read cover to cover the Spectrum magazine. And it was fun just to find out what people are doing in other parts of the world and other areas of electrical engineering, electronics engineering. And in the early 90s, it was just, the field was just taking off like crazy in the semiconductor industry. That's what I used to do in my previous first part of my career. I worked in Silicon Valley and making chips with my own hands. Used to wear bunny suits and have fun in the fabs. So I became blind about 15 years ago, and I started focusing more towards now electronics and looking into the fact that it is very challenging to make sure that the technology is available for the disabled and seniors. And to make that happen, there are a lot of initiatives with the engineers themselves can learn about it, can read about it, as well as find out new avenues of implementing this design so that they can put things together so it works for all populations. And not only this will improve your whatever products you'll be working on, whether it's a simple web-based project or it could be a complicated device or anything, but anything and everything is possible in terms of making sure it works for the disabled population. I myself worked on developing the world's first reading machine for the blind in partnership with Ray Kurzweil. And by doing some, by just stretching your imagination a little bit more beyond what you're normally working on, you'll be amazed how much your technology is capable of, and there are so many new possibilities will emerge. You yourself will be surprised. So whenever you guys are working on any kind of projects, whether be it your term project or your senior project, kind of have that inclusion in mind, that how can you make sure that this device or this application, whatever you're developing, can also work for people who are disabled, and it's a lot of people out there who work in this area. And at IEEE, we are initiating, have a lot of initiatives in accessibility. They are all over the place. At the same time, accessibility is something which still needs to be engraved in a lot of the organizations where you would end up working ultimately. So next year, and this is me, Bruce, and a few others, we will put together a program together, a conference on accessibility, which will portray on how accessibility can be part of your design, part of your implementation. So IEEE has put up conferences in accessibility in the past, but what we want to make sure is that these kind of things translate into real life, into real people's lives. It impacts everyone's life sooner or later. So thank you very much. Reach out to me if you have any issues. I do come to campus. I graduated from here, MIT, about 3 years ago from System Design Management program. And I do consult to different groups, as well as I am setting up my own startup called Easy Alliance. It's called easyalliance.org. And we are putting together so we can consult to companies, to individuals, to organizations where they can implement accessibility across the board. It's a lot about awareness, spreading the word out there, but we are working through. So thank you so much, and reach out if you have any questions or issues. Thank you.
My name is Harold Staab. I'm with ABB Corporate Research here in the US, and it's my pleasure to be here today. Thank you very much for the opportunity to be here, and thank you also for the opportunity for ABB to sponsor this very interesting and very exciting event. So we are very happy to be part of that. I would like to, my apologies for turning around once in a while, but I have to read what I'm actually going to show you. I would like to give you a short introduction to our company and also to the place where I'm working at and what we are doing and what ABB is all about. ABB is a global company, and I'm sure several of you have maybe heard of ABB. What ABB is doing is, in very simple words, we are doing power and automation technologies, systems, products, and all that for our customers are the utilities, industries, and also transportation infrastructure. And we do it globally. Our company is originally from Europe. Its headquarters is in Switzerland, and it has been a merger of a Swiss and Swedish company in 1988. And it's actually done here. These two companies, they merged to ABB, and the A from ASEA and BBC, the BB from BBC. That's where this name comes from. We have around 145,000 employees worldwide. We are operating in more than 100 countries. And our 2013 revenue was 42 billion. It has gone up since then a little bit. Also in North America, ABB is present, and currently about 20% of the whole company is located here in the North American region, and it is still growing very strong compared to what it was like maybe 5 or 10 years ago, since ABB was originally a European company, but our North America footprint is now strong and getting stronger. In fact, the US side of ABB is the largest country organization within the company now. So very exciting. More than 30,000 employees at ABB in North America. Give you an impression of our footprint in North America. So we are present in countless locations. And what is also part of ABB since less than 5 years are two American companies, Baldor and Thomas & Betts, which have been acquired by ABB in 2012 and 2013. Where do you find ABB technology? It's on many places where you don't expect it, and where even I did not know until I saw this slide and until I learned about a little bit more about the products and technology. So there are components orbiting the Earth. We are underground, deep under the Earth. We are crossing the oceans. We are on the seabed. We are in many parts of industries and infrastructure. One slide about our history. It started in the late 1800s when electrical technology and electrical machines became like the big technology boost at that time. And since then, many things have happened, and we were part of many innovations and many parts. But it's all about electrical engineering, about the power infrastructure, and about automation. And here's another example of one of our recent innovations, which we are really proud of. It's called Yumi. It is a dual-arm robot, and it is designed to operate safely next to humans in factory environments. So we see ourselves as one of the world's leading engineering companies, and our key focuses again are energy and automation. And we are trying to provide solutions that make you use energy in a more sustainable and more efficient way, and also to use to increase industrial productivity with our automation products. Energy efficiency is actually one of the large things and one of the main drivers where we want to be part of, and where we have a lot of innovations to show. This is just one example of where you can work in saving energy and increasing energy and efficiency, and it's actually, there are many parts along the electrical power side, where from production of energy up to the use of energy, where you can actually save a lot by simply increasing the efficiency. And wind, hydro, solar, and wave, these are the renewable energies where also ABB is getting very strong in, and we are trying to put a lot of strategic focus in these areas. Now, I want to show you a little bit about ABB Technology and ABB Research and Development, and this is actually where I'm working at. And the fact that ABB invests a huge part of their annual profits into R&D tells you that we see ourselves as an innovative company, and we want to be innovative in order to stay ahead and to stay in the markets as well. ABB Technology is, so there are 8,500 people worldwide, and we are part of what is called ABB Technology, which is all research and development of new products and solutions, as well as the more strategic side of R&D. And this more strategic side is called corporate research, and that's about 10% in turn of this, so around 800, 900 people worldwide are working in this. And I've already talked about that. And ABB Corporate Research has 7 locations worldwide, so also a global footprint with some emphasis to Europe because it's a European company, but the US part of it, which is located in Raleigh and in Windsor, in Connecticut, where actually I'm working at, is growing strongly. And within this corporate research, we are focusing on what we call research areas: control, communication, sensors, etc. So these technology areas, they pretty much cover what ABB products and solutions are all about. And what we are doing in particular, we see ourselves more as the strategic side of R&D. We are not developing products, but we're doing strategic research, and we're developing things that might become products in 5 to 10 years from now. So it's a very, very exciting environment to work in. Here's just a few more details about these research areas. And actually the Yumi robot that you just seen, this came out of corporate research as well. Also, within corporate research, we have a lot of collaboration with universities, including MIT, of course, and many more worldwide. And this also helps us to stay in close contact with the latest and greatest in technology and R&D. And of course, also to find the best talents for our company and make them excited, and we hope we can win them to work in our company. If you are interested in ABB and the opportunities, please check out the website here. We have tons of open postings out there both for regular jobs as well as for internships and training programs. So that might be a very, very interesting point for you to look into and to do maybe one day. So I would like to thank you for this opportunity, and I wish you all a great day and a great Sunday of this conference. Thank you very much.
Okay, so I'll stay here because that's where the microphone is. So first question, which I think is exciting, is where are you from? And what's interesting about this question is it's somewhat open-ended as to what does it mean. And you may answer, where are you working? So as you heard in the introduction, I work at Analog Devices. I'm often telling the story about IEEE events, especially if I've been coming from an IEEE event such as this one, then I'll describe some of the IEEE activities I've been involved in. And you heard from Sunish, we're looking to build a conference, build on one that was held previously called Accessing the Future at Northeastern University, and to take that forward with the partnership of the Consumer Electronics Societies, the IEEE Life Sciences, and others. Also, where are you from? It could be where did you grow up? So I was going to share that I grew up in Montreal, in Canada, and I was then an Ontarian for 7 years when I was a student at the University of Waterloo. And I've been living here in Boston for 21 years, and I'm actually a student here also as part of the Advanced Study Program, so I have a connection with yourselves here at MIT. Another part of where you're from, again, could be, where do you live? And so currently I'm living here in Boston, Brooklyn. And dragons are really popular in my family, so when I shared some of the photos from yesterday's session, My 3 kids, I have 2 daughters and a son, they were extremely excited to see more dragons being brought into IEEE. So that could be part of this year's new initiative. So what I wanted to share today was a little bit of a technical story. So this is an example from projects that I've worked on with a group that does medical imaging. So Analog Devices produces chips and modules and systems that go into electrical systems. It was exciting to see some of the slides from ABB. That's one of our partner companies, and you can see if you take parts and components and enable electronics, some of what can be done with those technologies. And so I was just going to take one example here from product teams that I worked on. And part of what I'm interested in at this time is the process of design. So how do we take new technologies, advanced technologies, and then translate that into products and that can be brought in to make changes depending on what's needed. And so in this case, I had a colleague, Brendan Cronin, help me put this set of slides together for the current work that's happening in medical imaging and what's happening in the world of the device technology and why does that matter in the case of medical imaging. So here's sort of the general process that we use in bringing new technologies into the world. There's understanding critical needs, so what is driving, what's the most challenging part where there's opportunity to make improvement. Based on that, what are core technologies? So this is sort of the what's in my bag for the company, or some people call this also what's in the wheelhouse. So what are some things that we have that are technologies that are going to provide capability that can't be achieved in other ways. And in the case of Analog Devices, there's a number of those. Of course, the history of the company was founded here by Ray Stata, so we're in the Stata Center. And Ray Stata was a student at MIT, and together with his college roommate, Matt Lorber, had founded Analog Devices, so it's the 50th anniversary of the company. And they got their start by taking individual transistors and building them into a small amplifier. And so the benefit of that is, number one, if you need an amplifier, you can get that part. But in addition, the design of that amplifier was built in such a way that it could do more than the sum of the parts. And so that knowledge is embedded actually inside the box. And if you're the customer, number one, you can order that part, you can put it in. But even more importantly, you're essentially accessing the knowledge that has been built into that part. And that's been the history of the company to expand on different ways of embedding knowledge into products. And also in transmitting that knowledge and working with customers, how can they use that and then apply it at the system level? And then on the right-hand side, in this particular example, you can see 2 kinds of technology. So there's the imaging, the chips that are on there, but there's also the flex. That's the material that's going to allow that chip to connect with the greater world. And in fact, just recently, we had a visit from the group here, Brian Anthony, that's in the electrical engineering and the mechanical engineering department. So you met yesterday when David was describing some of the activities here that are centered at MIT. Brian Anthony was visiting at Analog Devices and describing an initiative to look at flexible manufacturing. And that's an initiative that's working with several universities across the US and several industry partners. And this is one of those areas where new technologies are becoming available that are providing a significant advantage in what can be achieved. So in the case of medical imaging, there's a variety of different ways of looking into the body. So this can be used for diagnostics, it can be used for research to understand how the body works and then to improve upon it. There's several different types of machines. And typically, a lot of these machines that do imaging are very large scale, and it needs to be in one place inside a hospital building, and you have to go there in order to get that type of medical treatment. So then people ask a question, and this comes sometimes from within the company, sometimes from customers, sometimes with physicians. So a physician is there here at Mass General Hospital, for example, they have a radiology facility, and their question is, how can we take the hospital to you? So can we make it portable? And so on this slide, you see an example. If you could take an ultrasound or a CT scanner and reduce it into a handheld device, then you can bring the treatment or the diagnostics to the patient. In addition to this, there's a strong need for precision in electronics. So in the case of a CT scanner, it's actually using X-ray to image the body. And so there's a trade-off there. While the machine is operating, your body's actually undergoing the radiation from the X-ray. And you need to have a certain amount of that in order to be able to get the good quality of the image. But if the precision of the data converters can be improved, or if the optics can be improved, you can either have a lower dose of radiation for the same quality of image, or you can have less radiation for the same quality of image, or for the same radiation, you can get an improved quality of image. So overall, as we can advance that frontier of technology, we can put that to use, and the use can depend on the situation that we need. And this was an example of that particular product, and how by integrating both the packaging and the circuitry, we're able to get that kind of an advance. And this here, again, comes back into, so there's a sort of, in the systems engineering world, as Sunish was mentioning, the systems design management, so we recently brought a team here to investigate, so how can we learn more about the nature of systems engineering? There's a principle of being able to take problems, break it down into smaller pieces, solve the piece of the small problem. But if you're not done at that point, you still then need to integrate those parts and validate as you put them together that you're getting the capabilities that you need. So that's a part of ongoing process of bringing design, manufacturing, and products into the marketplace. This we talked about a little bit. And this again speaks about, for improving products over time, we need to really focus in on the design cycle. How do we match delivering to that potential with the time that's available in the project? So I just wanted to end again with the two questions. So as you go forward from this conference, people ask you, where were you this weekend, where you're coming from? So you'll have the opportunity to describe what interesting experiences, what did you learn, what do you want to do next? And I just want to share one last story about the what's in my bag, part of the other question I want to share with you. So I was traveling with the team. It was engineers, physicians, and entrepreneurs, mix of people from the Boston area, from MIT, from other universities, and we had gone to India, where we were working with counterparts from the Indian Institute of Technology, from several universities in the region, and physicians and doctors and entrepreneurs and engineers. But I happened to find myself in the car going from one event to the other, and so I was the engineer in the car. I was with a physician, the doctor from the MGH radiology group actually that I was describing, an entrepreneur who had started a business with his dorm roommate that went on to a very successful acquisition. And while we were in that car, of course, I had been doing tech things and giving people connectors and memory sticks and whatever was needed. The entrepreneur wasn't feeling so well, and so the physician said, well, I have what you need in my bag. I've got first aid kit, I've got medicine, I've got pain, whatever you need. And so this was good. This is something you may see. But then my friend Pete, who was the entrepreneur, he said, Bruce, I think you've been talking all the time. You haven't really sat down. Did you get lunch? There was lunch, but I think you missed it. I said, you're right. And I'm really hungry. He goes, well, I have what you need. So he reaches in his bag, and you know what he's got? Power bars. I'm not talking about the electric power bars. He's got actual granola bars, a whole stack of them. And so I found that the point of the what's in my bag is not only what you have, but it's what you bring with you that is then going to help give you the capability to help others. And so that's sort of true for yourself physically, what do you have? It's also true in sense from personal nature. So what is the capabilities and the skills that you're developing yourself that you're then helping others with? And that's true also for organizations. So what are the strengths of capacity that we have and that we're developing? And that's really what things come back to. And maybe just one more statement to connect back with Ray Stata. So at one point, he had founded an organization called Center for Quality Management, which was to engage across organizations, industry, academics, and others. And he had said that the only continuing strength of an organization is the ability of its people to learn. That's really what gives sustainable advantage. So I'd like to thank you again for coming, and I hope you will go forward and use these questions in your next steps.
So what I wanted to do is kind of give you an overview of what it might be to work in industry. So you can see that I gave you a subtitle, I love my job. And if you want, you can ask me a question about that.
Is it true?
And it's been true many times. Not always, but many times. Most of the time. And I also show two affiliations, and I'll talk a little bit about that too. So let me start with this here. So in 1994, Raytheon closed its research division, which might be kind of a weird way to start a talk. So why do I bring this up? I worked there, so it was meaningful to me. So I was 15 years into my career at that point. So mid-career, I was well into my career. When I looked around, there were a number of people, quite a few people in that division that were ready to retire. So it was fine for them. But when I thought about where they were, the Raytheon Research Division originated in the early 50s. It was kind of a post-World War II phenomenon. And there was this whole generation of engineers there that had spent their entire careers at the Raytheon Research Division. A really nice, sheltered place where you could do lots of interesting work. And I knew that wasn't going to be the common thread in my career. I wasn't going to be working in the same place for my entire career. So I'm going to give you a view of what I've experienced through my career and what kind of things, dynamics you might experience. But it's not going to tell you what your career is going to be like either. And I don't know what the common thread will be in your career. You probably will have one. Time will tell. So the common thread in my career is on the periodic table here, gallium arsenide. So that's what I got started with, and that's what I've continued with for my entire career. So if you go into Explore and you put in gallium arsenide, IEEE Explorer Library, the first few papers you'll see are from 1958. So I was born in 1957, so we grew up together, me and gallium arsenide. So when I got involved in gallium arsenide, and really up to the point where the Raytheon Research Division closed, there was this statement that we always made. Gallium arsenide is the technology of the future, always has been, always will be. That turned out not to be true. So when I started out in gallium arsenide, the first significant thing I did in gallium arsenide was work with impact diodes, an archaic thing that probably nobody learns about anymore. So these are diodes. You can make them out of silicon too. Gallium arsenide is more efficient. If you bias them into breakdown, you get negative differential resistance. So you can make an amplifier. You can make a reflection amplifier. So you need a circulator. It's kind of a pain to work with. I was working at 44 gigahertz, in which, still a pretty high frequency. It certainly was back then. We made 2 watts. We had cavities machined out of copper and sometimes out of brass. So I had to be good at drawing mechanical drawings and giving them to a machinist. And when we tuned these things up, we did some computer work. We had some analytical tools in the lab. But, when we measured these things, I had to calibrate my test system with a calorimeter, which basically compared heating water in a waveguide to what a resistor does. That's how we calibrated. And to optimize these things, we had 600 grit sandpaper, and we polished shims of copper to tune this thing in. But we made 2 watts, which was pretty darn good. Turns out, if you have a piece of waveguide, and you forget to put the load at the end of it, and you have 2 watts going down it, free space isn't a bad mismatch. It actually propagates pretty well into free space. If your hand kind of brushes by it, if you feel heat, that's enough. So that was cool. But then I moved on to something that was really cool, and that was starting to make integrated circuits. And it turned out that, Raytheon was one of the early leaders in developing gallium arsenide technology. There were just a handful of companies that were out in the forefront, and pretty much anything we did was new, which is a lot of fun. So on the top left is a phase shifter. The first chip I designed was a phase shifter, 3-bit phase shifter. 180 grit bit in the middle, and then there's a 90 and a 45 on either side. And it worked. We had very primitive, my design file was done with a text file with nodes and element statements for what the different elements were. But it worked. It shifted phase. The loss was pretty close to what I had expected. So it was very successful. I wrote a paper, my first paper. I had been a co-author on an impact paper. The 2 bits on the left and right side, I came up with a new circuit topology for a phase shifter bit. Still being used today. I wrote a patent disclosure on it. Raytheon decided not to pursue a patent on it because the bit in the middle, actually my boss had designed for an earlier phase shifter. And the claims had been written quite broadly, so they decided that his patent already covered my idea, so I didn't get a patent out of that one. The next one over is a switch that went from a few megahertz all the way to 40 gigahertz. And it's not a great performance switch, but it was the first one that did that. And it actually made its way, I'm a microwave RF guy, if you haven't figured that out yet. I belong to the MTT Society. That part made its way into the MTT historical exhibit. So every year at the big conference that we hold, you can see that part. The next one's a distributed amplifier. Did a bunch of those. I don't know if you learn about distributed amplifiers, but it's a pretty cool way to get a very broadband amplifier. One day I was flying home from the West Coast, and I just had this idea about how I could take two distributed amplifiers and instead of cascading them, basically put them together in a matrix, make a matrix amplifier. And I thought that was a brilliant idea. It was a really, really good idea. So the next day when I got back to my office, I got out my lab notebook and I wrote it all up, and I actually had a colleague witness it because I knew this was a great idea. And then the next week, the IEEE transactions on microwave theory and techniques came out, and a guy named Nicholas at Watkins Johnson published a paper on that very idea. And he also called it a matrix amplifier. So, I mean, too bad. It turned out to be a really cool idea, but it doesn't work that well, so they really went nowhere. My phase shifter, you still see it all over the place, so that's pretty cool. And then the other thing is just a bunch of distributed amplifiers together. So I thought this was pretty exciting, and then something else happened. So, you know, I'm a circuit guy. The device guys started to take advantage of heterojunctions. And all of a sudden, transistor performance improved. So I'd been working with FETs. The improvement of the FET was called the HEMT and then the PHEMT. And all this did was basically increase mobility. So you got higher performance transistors, and you can trade off frequency for breakdown voltage. So really, it improves the gain. Meanwhile, a bunch of other researchers were working on bipolars. And you know, people have been dabbling with bipolars for a long time in gas, but around the late 80s, they really started to work well. And in fact, I think the guy that really gets credit for making the HBT, gas HBT work is a fellow named Peter Aspeck, who was at Rockwell Science Labs at the time. Now he's at UCSD. And I don't know if there's, yeah, okay, there we go. All right. So on the bottom I showed you some diagrams of the cross sections of the two types of transistors, and I'm not going to get into that at all. But our big conference every year, the International Microwave Symposium, in 1989 featured a panel session with advocates for HBT and PHEMT. And this was an emotionally charged, I mean, you couldn't imagine a more exciting event than a panel session at a technical conference. And we had Phil Smith for advocating for PHEMT, and Burhan Barakaraglu from TI advocating for HBT, and they really got into it. It was exciting. I was a PHEMT guy, although I've probably spent more time with HBTs now than PHEMTs. So things started to become pretty serious with gallium arsenide, although it really wasn't successful yet. The military had pretty much funded all of it up to this point. At Raytheon, they did something for the Army in the early 90s into 95, creating a phased array radar called GBR, ground-based radar, for a missile system called THAAD. It was just a demonstration project. But what you see on the top is a module, and the large black rectangles, and there's probably, I don't know, 10 of them in there, they're all pieces of gallium arsenide. And thousands of these modules populated a phased array. So you see on the bottom picture, the frontmost trailer is a phased array antenna, with active phased array antenna, which is a big deal. Had thousands of these modules, and you could steer the beam electronically. it wasn't terribly efficient. I don't know that it's ever really gone anywhere at this scale, but there's lots of these kind of things out there now. So the front trailer is the phased array. The trailer behind it is all the other electronics to make the system work. The trailer off to the left side behind it is the cooling system for the antenna, because it's only about 10% efficient. And then the things in the back are all the power supplies to run the thing. So not exactly the most portable thing in the world, but you could actually move it around. All right, so now we're at 1994, and the research division closed. So was the Cold War a good thing? So, I started. I went to college in 1975, and that was just as the Vietnam War had wound down, and companies were laying off electrical engineers everywhere. My dad was an electrical engineer, and he actually got laid off. I loved engineering. I was going to go to engineering school anyway. In 1979, when I graduated, things had completely turned around. You couldn't hire enough engineers. I had lots of job offers. It was great. It was the Cold War that was kind of funding all this. And, the Cold War ended. And that's really why you saw these reductions in military spending, and that's why probably the research division closed. And we really saw lots of corporate research facilities closing around that time. And it really seemed to me that maybe it was the end of corporate research. And for a lot of companies, it was and still is. But we see lots of other companies that haven't done that. You heard about ABB earlier. Look at Google Labs, for example. There's lots and lots of good corporate R&D out there now. So I was at Raytheon. I stuck it out at Raytheon for a couple more years. The corporate culture at Raytheon for the years that I had been there had been great. I really enjoyed it. It was great people doing great things. Most of my time was a research division, but I also worked in one of the other divisions. But it quickly got bad. It got to be a very unpleasant place. So corporate cultures can decline very quickly. Doesn't take long at all. I have lots of friends still there. It's actually quite nice again, but it took a long time. So you can screw up a corporate culture in a hurry, but it takes a long time to establish a positive one. All right. So I moved on and did a few different things. To me, it was useful to sample different organizations and different ways of doing things. I worked for a small company, worked for a really big company, and then I ended up where I am now. So let's look at gallium arsenide again. So you can see we start in 1990, go up to last year. And so this is sales dollars of gallium arsenide worldwide. So it's basically gone 30 to 1 over that time period, so pretty significant growth. I put rough cost per square millimeter to make gallium arsenide, and so it's dropped by about a factor of 10 over that time period, maybe even more than that. So if you look at volume of gallium arsenide made, this is 30 to 1 in dollars. Volume, it's 300 to 1, 500 to 1. So gallium arsenide has taken off, and you all have gallium arsenide in your pockets, I promise you.
Oh, no.
It's true. So let's look at this curve in a different way. So I showed you a military example. That's not why gallium arsenide has taken off. This is why gallium arsenide has taken off. So we start at the very beginning in 1990-ish. So that's an old Motorola flip phone. I don't know if any of you would have ever seen one. Back at the time, my boss had one. I didn't carry a phone with me. It had some switches, some gallium arsenide switches in it, and that was it. But that was big for gallium arsenide at the time. And there were really two main suppliers, Alpha Industries, which is now called Skyworks, and Macom, both in the Boston area. And this one guy named Dave Strickland knew all the customers at Motorola, and the two companies would kind of steal them back and forth. So he ping-ponged between those two companies and made more money each time. He was not a great engineer, he just knew the customers. And then, but Motorola was fixated on their analog technology. So that's an analog cell phone. Talks with an analog modulated signal to the tower. The Europeans came up with GSM, digital technology, 2G. Analog was 1G. And Motorola took a long time to realize that that was a better thing. So by the time that happened, Ericsson, which is the second phone you see there, was number one. And Ericsson eventually got to the point where they used gallium arsenide power amplifiers, using FET transistors made, for the most part, by Digix, a company in New Jersey. And so you start to see gallium arsenide taken off more. Then in the late 90s, Nokia, which is a little company in Finland, mostly known for tires and wood products, but they have a small electronics operation, they decided to take a different view, and they've been doing some cell phones, but they decided to take a different look at it. And their thought was what really matters isn't talk time, because that's what everybody was advertising. What really matters is standby time. So we can make a phone that, you're not going to be talking that much. We can make a phone, you can charge it, and you can be good for 5-7 days by reducing standby power consumption. And one of the ways they did it was to reduce the voltage. So the phones have been operating 5-6 volts. They went down to a 3-volt battery, which reduces power consumption. For all those functions that are going on in standby, you don't need high voltage. 3 volts was enough, so the power consumption drops quite a bit. But they needed power amplifiers that could run at 3 volts. And guess what worked well for that? Gallium arsenide HBTs, which is what my company was doing. I wasn't there yet. I wasn't at RFMD. Digix stubbornly stuck with the field effect transistor power amplifiers, and they have never recovered. They're still around, but just barely. So Nokia took off at this point, and within a few years, Nokia commanded between 35 and 40% of the cell phone market worldwide. And it looked like that would never end. They cranked out one phone after another. Your parents certainly owned some Nokia phones along the way. And we supplied to them. So phones became cheaper and cheaper. The electronics became cheaper and cheaper. Volume kept going higher and higher. But it was getting to be a challenge to kind of keep up with the demand for, ever smaller, more capable products. And then something else happened. So I've kind of run through some of the things that happened with all these other devices. I think I've pretty much covered it all. Yeah, camera phones were in there. And then in 2007, this thing called the iPhone shows up. It was interesting, but did it really matter? So at that point, the world was consuming maybe 1.5 billion phones a year. Right now, it's 2 billion phones a year that get consumed. We've saturated. I mean, pretty much everybody has one. So this is just, people replacing phones at this point. So the iPhone came out. The iPhone sold millions. But Nokia was selling hundreds of millions of phones. So does the iPhone really matter at that point? Well, I think we all know that it did. From where I was sitting, you look at the iPhone, the emphasis was on the apps and the display and things like that. The electronics really didn't seem to be that important. Certainly the RF electronics didn't seem to be that important. So it got to the point where you think, we might be in trouble kind of in the RF world. But one thing that was pretty clear, and Apple knew this, they negotiated a deal so that Wi-Fi was in the phone. So all those Nokia phones I showed you, towards the end they had Wi-Fi in them. But the US operators insisted that when they sold those phones to their customers, Wi-Fi was disabled or removed. They didn't want you to use Wi-Fi, they wanted you to use their networks. Apple says, no, we need to have the Wi-Fi functional. And it's true because See, the first iPhone was called the iPhone. The second one was called the iPhone 3G, right? So if that's the iPhone 3G, what did the first iPhone use? 2.5G. If you've got your iPhone right now and you see it switch to 3G, what do you think? You think this sucks. If you had the thing before 3G, how did you think it worked? You needed Wi-Fi. There wasn't network capacity, and certainly you weren't getting the kind of speed you needed. So bandwidth was suddenly very, very important. And the network users, operators didn't have the capacity. So what did the smartphone era mean? Well, first of all, there's a famous message that the new president of Nokia sent to his employees in 2011 called the Burning Platform email. You can Google it. Stephen Elop was his name. And he told a story about a worker on an oil platform in the North Sea. North Sea is a brutal environment. The water is ice cold. You can't survive for more than 30 seconds in that water. But the platform is burning. So you would never jump into the water because it was near certain death. But the platform is burning. Not jumping is certain death. So you have no choice but to jump. And that's what he was saying Nokia had to do. Our platform is burning. It's the end of the road if we keep doing what we're doing. We're going to start making Windows phones. And so Nokia doesn't exist anymore. How many of you have Windows phones? Yes, thought so. Although they work pretty well. Nothing wrong with them. So Nokia's disappeared now. Literally gone. I mean, Microsoft bought them, and they even brand the phones Microsoft now. So Nokia doesn't exist anymore as a phone company. And they got rid of tires. I think they still do some other things. They certainly do wireless network stuff and are a customer of ours. Now we have 4G. We're going beyond 4G. There are now 44 different frequency bands worldwide that you can use for cellular communication. Modern cell phones have 24 bands. The next generation will have more. That's a lot of complication. There's amplifiers and tuners and switches and filters. There's a lot of RF stuff in a phone right now. So my old thought was, oh, we're doomed. It was wrong because it's more complicated than it ever was. The antenna, so you take a look at a phone like this. It's a metal case. There's two antennas here. I don't know if you remember the grip of death on one of the iPhone versions. You're covering a very large frequency band. Antennas are a tuned device. They don't operate well over a large frequency band. So in order to make these crappy antennas work well in a cell phone, there is an extra piece of electronics in there called a tuner. Yet more stuff that we can sell. So the bottom line is we have lots of stuff that we're doing right now, and even more coming. So the latest generation of phones actually can transmit and receive simultaneously on multiple bands. Even more complicated RF. So one of the leaders of my company likes to say we've gone from dimes to dollars. And what that means is if you take a look at an old phone like Jeremy's, there's literally dimes worth of RF content in it. And if you take a look at an iPhone, there is dollars and dollars worth of content in it. And, $2 billion a year, that's a very large market. So let's take a look at the iPhone 6S, which just came out. So you just go to iFixit, you can see what's in these phones. So first you see on the left side, pretty picture of the phone, and then you can see in the middle, a phone popped open. So the biggest thing that you see in that phone is what? The battery. That's why the watches have a challenge. It's not the electronics, it's the battery, right? So if you really want to make an impact, work on battery technology. Batteries improve a few percentage points a year, so progress is continually made. semiconductors, we have to make a more complicated device and sell it for 15% less than last year every single year. It's unrelenting. That we know how to do. Batteries we don't know how to do. And then there's a phone board that's wrapped around the motherboard, that's wrapped around the battery, and that's all the electronics on that board, and you see two sides of it. So if you look, let's see if I can find my way over the screen. Okay, so this portion of the board and here, so almost a third of it, that's all RF. So there's a lot of RF stuff in these phones. The latest thing that's happened is something called envelope tracking. So you make an amplifier, you run it off of a power supply, and that's what you see on the left side. So you have a modulated signal. So these are complex modulated signals that you've got going on in your phone. So it might be transmitting at 1800 megahertz, but there's a signal modulated above it, and it'd be 10 or even 20 megahertz of bandwidth. So when the amplifier is operating well below peak voltage, which happens when there's all this modulation, that's just wasted power. And so that's the yellow. That's just energy that's being thrown away. So the latest thing is we have an envelope tracking power supply. So the supply voltage is reduced to what the envelope requires. So the bandwidth of the RF is now about 20 megahertz. The envelope needs to be able to respond even faster. So the power supply is now an RF part. So even more complications, more work for us. And if you ever do anything with amplifiers, so the best thing to do is to decouple the power supply. You put a big capacitor there, it helps stabilize stuff. But now this thing is moving at tens of megahertz, so we can't even decouple the power supply anymore. So it gets to be challenging. That's good for us. I mean, people complain about, oh, geez, the new spec is so hard. Great. And if it wasn't challenging, they wouldn't be paying us for it. But if you look at the pieces of the pie, there's kind of a green piece. That's all the military spending, about 5%. And there's the purple part, which is fiber optics. And really, the rest of it is all wireless of different flavors. Blue being cellular, the red being Wi-Fi, and the other pieces being appliances and stuff in cars, etc. So it's really the commercial that has taken over. The purple part that's Wi-Fi. I don't know if you remember when I showed you the bar graph of the market. There was kind of a peak in 2000 and then a drop off. That was the popping of the tech bubble. The internet had just taken off, and there was this expectation that there'd be just unending demand, and it was crazy. It was a bubble, and it burst. There was so much fiber optic stuff built that it took more than a decade to recover from that. And that's why there was this sudden drop, because the fiber optic dimension of it disappeared. Okay, so my life has been primarily all about gallium arsenide, but not exclusively. And there are challengers to gallium arsenide. So gallium nitride and silicon carbide are very interesting materials and coming into their own recently. Higher voltage materials, bigger band gap, better thermal conductivity. So you can make really nice high-power devices with these technologies. So the military is very, very interested in this. For a handset, the cost is really the primary concern. And these are expensive technologies, and the powers in the handset aren't that high. So maybe not, or not for a long time anyway. But military applications, infrastructure, so cell towers, things like that. Cable systems, broadband, line amplifiers, gallium nitride looks like a good solution there. Silicon on insulator, my company does a lot of silicon on insulator, has really replaced gallium arsenide. It's the preferred switching device. It's much better. Then we have silicon germanium and CMOS. You can do lots of stuff with them. A silicon germanium transistor is pretty equivalent to a gallium arsenide bipolar. It's cheaper, but it hasn't taken off. I mean, we make silicon germanium power amplifiers and we sell them into handsets. But the issue really with silicon germanium is, gallium arsenide wafer takes 2 weeks to fabricate. A silicon wafer takes 2 months to fabricate, and the mass cost is much, much higher. And we have to respond quickly to each new generation. You know, the new generations of phones come out every year. We need to respond quickly, and it's almost impossible to do that with silicon germanium. So gallium arsenide wins because it's a simpler process, not because it's a cheaper device or a superior device. And then finally MEMS, which you may or may not have heard about, will probably replace silicon on insulator in the coming years as those switches become reliable. The switching that goes on in a cell phone needs to do billions of cycles, so mechanical devices are a little tougher. So getting the metallurgy just right is a bit of a challenge. So then we get to the next milestone. So I work for RF Microdevices. RF Microdevices, incidentally, was a spin out of Analog Devices. The founder and my first boss at RFMD worked for Ray Stata, and it was a friendly parting of ways. Ray kind of helped them get their start. So another interesting connection there. So in 2014, these two companies decided they would merge. And so that's something maybe to be a little nervous about. But really, when you looked at it, we needed each other. At RFMD, we had no filter technology of our own, and filters are becoming ever more important. TriQuint had some great filter technologies. We had a great factory, so we could really produce lots of volume in low quality, in low cost. They outsourced all their manufacturing. I mean, they had the fab, but the rest of the manufacturing they didn't do. So they needed us. So it really ended up being a great merger. For some people, it was kind of a challenge. For engineers, not a problem at all. We were actually working with complementary products. So exciting and work, and the work continues. But pretty interesting. So this is a name that was picked. You have to ask some consultant why they came up with this. One of the reasons is, you need to be able to get the URL, and any rational word is already taken. So this is what we're called, Qorvo. So that's where we are today. All right. So let me just talk a little bit about the IEEE. I just got my new membership card. I'll pull it out. Prove it to you. So I was kind of surprised when I got it. It says I've been a member for 39 years, which really surprised me. But it's true. And I realized that I'm 2 years away from being a life member. Which is good, but... So I've been involved in the IEEE for a long, long time. And there's value in being an IEEE member. If you're in the U.S., you can buy discounted life insurance. And if at this point in your life you're thinking about that, come talk to me because you shouldn't be. But the real value of being an IEEE member is in being an engaged, involved IEEE member. Just being a passive member has minimal value. Being an engaged member is where all the value comes from. And there's lots of places you can get involved. I really started out, with my society, and then got into conferences, and now I'm chair of the conference committee for all of IEEE. But there are lots of places to get involved, and the key is to just find the place where you fit in best and get involved and continue to be involved, and really become an active part of the community.